All right, let's get into it. We're about to talk about what might just be the longest, most drawn-out argument over maybe the most underwhelming object in the entire famous Messier catalog. It's been called the longest argument about the most boring object, but trust me, the story behind it is anything but. So here it is. This is the heart of the whole debate. When you look at these four bright stars, what are you really seeing? Are they a family, gravitationally bound and traveling together through space? Or is it something else entirely? So are they a family, or are they just strangers passing in the night? I mean, that was the big question that had astronomers scratching their heads for centuries. And figuring it out tells us this fascinating story about how science actually works, with all the debates, the biases, and the long search for proof. Okay, so to get this, we have to go way back to the late 18th century and meet the famous French comet hunter Charles Messier. His main job was finding comets, but the problem is, the night sky is full of other fuzzy things that can really trick you. So to make his life easier, he started making a list of all the things that weren't comets. These fuzzy patches and star clusters. And this little Y-shaped group of stars, well, he thought he saw some nebulosity, some fuzziness around it. So it made the list as number 73. Yeah, but here's the thing. Right from the get-go, people had their doubts. And this is where we run into a classic case of, scientific inertia. Once an idea gets rolling, it's really, really hard to stop. So fast forward a few decades, the famous astronomer John Herschel points his telescope, which was way better than Messier's, by the way, at M73. And guess what? He sees no fuzziness. None. Just a couple of stars. But because it was already in Messier's super famous catalog, he kind of felt like he had to include it in his own. And that right there is a textbook example of confirmation bias, right? The thinking was, hey, if Messier put it in his catalog, it must be something important. And just like that, this little group of stars gets passed down from one catalog to the next, cementing its status as a real object, probably some kind of sparse open star cluster. Okay, now let's jump way ahead to the year 2000. This is where the debate really heats up. In this crazy twist, two different teams of scientists published papers on M73 within just a month of each other, and their conclusions could not have been more different. And get this is the wild part. Both teams were using the exact same basic method, plotting the brightness and color of the stars. But one team says, yep, it's a real, even if it's a sparse, old star cluster, and the other team says, no way, it's not a cluster at all. It's just a random lineup of stars. And this right here really shows you the problem. See these charts? They're called color magnitude diagrams. Now for a real star cluster, the stars should line up and form a nice tight sequence. Team Asterism looked at this data and just saw a random mess, a total scatter. But Team Cluster, they looked at the exact same messy data and said, hold on, if you squint, you can totally pick out a sequence of stars in all that noise. I mean, can you believe it? Same evidence, totally opposite conclusions. So we're at a total stalemate. The evidence they had just wasn't cutting it. Science needed a tiebreaker. It needed a totally new kind of data to finally solve this thing once and for all. So the first big clue came from something called proper motion. Just think of it as tracking the stars' sideways drift across the sky over time. Now, if they were a real family, a real cluster, they'd all be moving together, right? Like a flock of birds. But as you can see here, their movements are all over the place. That was a huge red flag for the whole cluster idea. But that wasn't quite the nail in the coffin. The real, indisputable smoking gun? Well, for that, we needed to stop looking at how they move side to side and start looking at how they're moving towards us or away from us. And that's where a technique called radial velocity comes in. It's like a cosmic speed gun for astronomers. Basically, they break up a star's light into a spectrum, like a rainbow. If the light waves are getting squished together, that's a blue shift. It means the star is moving towards us. If they're getting stretched out, a red shift, it's moving away. It's an incredibly precise tool. And the logic is super simple. Think about it. A real family of stars, a true gravitationally bound cluster, should be moving through space as a group, so their speeds, their radial velocities, should all be pretty much the same. If their speeds are all over the place, well, then they're not a family. They're just strangers. So that brings us to 2002. A new study comes out, and they do exactly that. They point their instruments at the 6 brightest stars in the M73 group and measure their radial velocities. And the results? Well, they were the final word on the matter.
Just look at these numbers. It's absolutely wild. These speeds aren't just a little different, they're on completely different planets. You've got one star racing towards us at almost 54 kilometers a second, while another one is flying away from us at nearly 35 kilometers a second. They have absolutely nothing to do with each other. They weren't a family, they weren't even distant cousins, total strangers.
And with that, case closed. The debate was over. Messier 73 was not a cluster. After more than 200 years, the argument was finally settled. What it turned out to be is something called an asterism. It's just a trick of perspective, a chance alignment. It's like the Big Dipper, right? Those stars look like they form a pattern, but they're not actually a physically connected group. They're just unrelated stars at totally different distances that happen to line up perfectly from our little vantage point here on Earth.
Okay, so after all that drama, you might be thinking, who cares? Why does this little group of a few random stars even matter? Well, it matters because this whole long, drawn-out story is a perfect example of the scientific method working exactly as it should. It shows that science isn't about knowing everything, it's a process. And most importantly, it's a process that's designed to be self-correcting. I mean, just think about the whole arc of this thing. It starts with a little note in a catalog about a fuzzy spot. That idea gets passed down for centuries. Then we get better tools, but even those lead to a head-on collision between two interpretations of the same data. And finally, a totally new type of evidence, spectroscopy, comes along and provides the hard, undeniable numbers needed to completely overturn something that was considered a fact for over 200 years. That's how it works.
And that kind of leaves you with a really interesting question, doesn't it? How many other facts that are written down in old books and catalogs are just sitting there, waiting for the right tool or the right evidence to come along and show us the real story? The tale of M73 is a great reminder that even the most boring things in the sky can teach us the most exciting lessons about how we learn.